Salutations, Internet. Good time zone. So, you'll note that we are starting a bit further zoomed out than usual. That is because we just have that many equations under our belt. We've talked about all of these things up to this point. And, that's really something to look at and be proud of. Because this is rocket science. This is actually rocket science that we're looking at right now. This is the benchmark standard for difficulty. There are things more difficult than this, don't get me wrong, but this is what everyone turns to and says, well, that's pretty difficult. And if you've made it this far voluntarily into the series, good on you. Congratulations. Take a minute to just appreciate all the stuff that you have accomplished so far. All right, and we're going to move on. This is actually about half of... I'm saying half it. I'm about halfway through my notes right now. And in fact, for today's material, I have a little note about the first test that is coming up. That's right, we haven't even gotten to the first test yet. This is all the base stuff. This is stuff that is important for moving on, but there's a lot more after this. And that something else that is after this is let me start off by drawing a diagram. All right. So we have the Earth, and I'm going to go ahead and put in Sputnik here. And that'll work. Hey, Sputnik. All right. We're going to draw our ellipse. And this is a great representation of everything that we know so far. If we know an orbit, we know everything that there is to know about Sputnik's position, angular momentum, energy, velocity. What kind of speed are they going to need in order to leave the Earth system from any given point? We have time of flights, we have orbital elements, we have everything that we need to know this. Which is why we are not going to consider it. Instead, if we look at a position for Sputnik, and then we look at let's try that again. There we go. If we look at a second position for Sputnik, and we know the amount of time that has passed between them, suddenly we have a problem. Because none of these equations that we have here will actually help us with determining a position, a time of flight, and a second position. This is called Lambert's problem. And this is going to be the topic of discussion for several videos in the series. This is a pretty big deal in the astronomical community. So if we had, going back to the second episode, the second video in the series, if we were given a position vector and a velocity vector, we can make an angular momentum vector. And from there, we can literally make everything else. But way out in space, we're not always given a velocity vector. We can be given position vectors for sure, but not velocity vectors. And to give you a real-world example of this, if you look at Oumuamua in 2017, that came from way out in space. And in 2017, we went, hang on, there's a strange rock that we've never seen before. We didn't know what its heading was, where it had come from. We just saw it and said, okay, this is where it is now. And then we came back to it sometime later and said, this is now where it is. Literally, this situation. And we were able to determine, okay, how close is it going to get to the Earth? Is it going to get close enough that we can send a satellite to it? Can we see how it will interact with the sun? Is it going to get all the way down below the Earth's orbit? These are all things that are very important if you want to study materials coming in from outside of the solar system. But we wouldn't be able to plan for those things if we didn't know what its trajectory was using this system. And there are plenty of other examples that I can use to describe beyond that. So that is the basics of Lambert's problem and the motivation behind why we want to solve it. Now, in my notes, I have 3 separate subsections here for how to approach it. And the one that we're going to be looking at today is going to be called the Lagrangian coefficients. Lagrangian coefficients. So something I want to address before I get too far is that I'm making this series of videos on this topic on the internet. It's really easy to say with a confident enough voice that, oh yeah, this is how you do it. Fair, but this is a really tricky problem in the astrodynamics community. There are entire PhD theses that you can pursue for this topic. So now that that disclaimer has been thrown out there, and hopefully there will be some understanding that the risk of mistakes is going to be significantly higher. I'm hoping that everybody keeps an eye out for those, and I look forward to future discussions on that. But the idea behind the Lagrangian coefficients is that we want, so if we want to have a position vector at any given time and a velocity vector at any given time. And in order to do that, we will use a position vector at an initial time and a velocity vector at an initial time. And if we use some linear combination of these, we can get the things that we actually want. So I say linear combination. For those who have not experienced linear combinations of things before, allow me to introduce you to it. So if we want an R of t, that is going to be equal to a coefficient f times the position. I'm going to write it as R sub O. These are equivalent now that I have officially defined that. And then we are going to add a G times V sub O. And similar for velocity, we will have an F dot of our initial position and a G dot of our initial velocity. And this is what linear combination means. These are the two terms that we are interested in using, and they are added in together linearly with some kind of coefficient on either side. What would make this a nonlinear thing, for example, would be to square one of the terms. But since we're not doing that, this is just a linear combination. And this is the Lagrangian coefficients approach. Let's give me some more space. So these are, this set of equations is not linearly independent from one another. And I can demonstrate that to you by showing, so we have an r vector and a v vector. Well, we've done that we've dealt with that before. We can make a specific angular momentum vector from that. And let me copy that over. R cross v. And I'm just going to expand. So one moment. All right. And then I'm going to scroll down a little bit more again, give my wrist some breathing room here. So to distribute that, will give us do an f times an f dot times r naught crossed with r naught plus an f times g dot times an r naught crossed with a v naught plus a gf dot, because for scalars, order doesn't matter, but it helps me with the vectors, because the order here does matter. V naught crossed with R naught plus a G times a times G dot V naught crossed with V naught. And this is, at first glance, this can look as though it's getting out of control, but let's remember that cross products are a little funky in that not only does order matter, but multiplying the same term does not do the same thing with vectors as it does with scalars. For example, a position vector crossed with itself is going to be 0. That's a 0 vector, as it is with the velocity vector. That is not a velocity vector, excuse you. Here we go. As it is for any vector. Very fortunately, that takes out half of our terms. That's not bad. On top of this, R naught crossed with V naught. Well, we've already defined it up here. That is the angular momentum. And to that end, V naught crossed with R naught. Because the order is reversed, so is the direction of the same value. It's just pointing in the opposite direction. Which means that after you apply all of that, you are going to get Fg dot times h, and then this one, because it's reversed, it is negated. So minus f dot g, because that fits better in my mind, times h. Now we can factor out the h, turn it into a scalar equation. 1 equals f g dot minus f dot g. And this is the constraint for the Lagrangian coefficients, which tells us that if we know 3 of these values, we can know what the 4th one is, which isn't a huge step, but it is a step. It is a step in the right direction. Let's take a moment to step back. Let's pause this for a second. A lot of people who are smarter than me spent way more time on this than I am about to, and they made some determinations on what makes sense to proceed forward. Right? So they decided that if you were going to use this approach, you would want to use a perifocal perifocal reference frame. And I'm sure that you use the word perifocal at least 3 times a day in your common vocabulary, right? So for everyone who doesn't do that, rest assured it's not that bad. We've kind of already been dealing with it. So if I were to draw a diagram, yeah, like that. And then space. We'll put Sputnik in here. Welcome back. So for a perifocal reference frame, we have pointing out of the periapse, pointing in the direction of the periapse, p hat. So that is the definition of where p is. It is pointing at all times towards the periapse. 90 degrees to that is going to be q hat. And then orthogonal to both of them is going to be the direction of w hat. And that comes out of the page, out of the screen, out towards your face. And since the technology for drawing that does not exist at this time, we're just going to use our imaginations and say that it's pointing out of the page. I'm not going to be using it a whole lot, but that is officially what the PQW, the perifocal reference frame, looks like. So if we were to do this, where we can define that, so at a position vector of r, there is an angle with the p direction of theta. This is looking very familiar, I'm sure. That is going to look something like this. PQW. It's probably going to be the only time that I actually use that. This. At this. Thank you. That is going to be r times the cosine of theta, r times the sine of theta, and 0. So that's what it looks like in vector in vector notation. But then to have it all on a single line, which is how I'm going to be dealing with it, really, that is going to be r times the cosine of theta in the p direction plus r times the sine of theta in the q direction. And then because it's plus 0 in the w direction, I'm not going to bother writing that. There's spoiler alert, there's not a whole lot of excitement that happens in the w direction. So I'm going to be ignoring it. At least for now. Will I stop ignoring it later? Who knows? Alright. Why did I start writing that? I didn't have to. So let's keep track of this. We're going to underline it in green because that's not really an equation that's worth putting on the equation sheet, but it is worth keeping track of. We have a position vector, which is great. Now we need a velocity vector. And a good way of doing that is just taking the time derivative of the position vector. Let me scroll down here. And we have v is equal to, and so both of these terms, both of these components in the p term can have time-dependent solutions, I guess. They are both time-dependent. So, it'll be r dot times the cosine of theta. And then I'm going to draw my triangle up here. I'm going to do this every time. That's fine. Cosine along the bottom, sine along the side. So at the beginning, cosine is going down. So it is minus r theta dot times the sine of theta. That is in the p hat direction. Awesome. Now we do the same thing in the q hat direction. R dot times the sine of theta. And then I know it's going to be r theta dot, but at the beginning, so we have sine increasing. So that will be a plus cosine of theta in the q direction. All right, awesome. Now, so we have this set up in velocities. We have r dot and we have r theta dot. And so with that, we can make it more complicated before we make it more simple by going over to our equation sheet and seeing that, hey, v sub r is the same as r dot. And we have r squared theta dot. If we divide out an r, we can have an h over r. So we have components for an r dot and an r theta dot. Let me copy those over. We have r dot is equal to, I have mu over h times e times the sine of theta. And r theta dot is going to be h over r, which we can make further complicated by realizing that r, we have an equation for that in the form of the orbit equation. We've been using it a lot. It's a good thing that we came up with that. So we'll have h, and then because it's inverted, the denominator goes up top, so that's 1 plus e times the cosine of theta. And that is all over, this would be p, but I'm going to use the h squared by mu, because there's already an h right here. So h squared by mu. And juggling things around, you can cancel out some of the h's. Move the mu up top, so you have mu by h times 1 plus eccentricity times the cosine of theta. And that's good enough to plug back in. So our velocity then becomes, oh boy, I'm going to need a bigger bracket. So that's going to become mu by h times e times the sine of theta times the thought I got past that, times the cosine of theta minus mu by h. I'm going to distribute the sine here, times the sine of theta plus e times the cosine of theta times the sine. Ooh, slow down. Times the sine of theta. And that's in the p direction. No, I better do that. I'll scroll down to here. Plus, again, I'm going to need a bigger bracket. So again, mu by h times e times the sine squared of theta, because we have a sine here and a sine here, plus mu by h. And again, I'm going to distribute. So times the cosine of theta plus e times cosine times cosine is cosine squared. E times the cosine squared of theta. All right. And now for my last trick, for this episode at least, I'm going to simplify it down as much as I can. So we have, at least for P, we have a mu divided by an H. That is going to be times, so we have an eccentricity sine cosine and eccentricity sine cosine. These will cancel out because if we distribute the negative, these will cancel out. So then we have minus mu by h times the sine of theta in the p direction, which is actually not too far from the r dot equation that we have, yeah. And then for the q component, I don't need a bracket that big. We will do, I'll tell you what, we'll do mu by h again. And then we have e sine squared and e cosine squared. When you add sine squared and cosine squared, you're going to get 1. So let's go ahead and do that. 1 plus cosine of theta. That is q hat. And I'm going to underline this in green for much the same reason that I underlined the radius. And I'm going to have this be the end of the episode because I don't want to record for 45 plus minutes. I think that that's going to be too long of a video. And I need to get caught up on my notes again to work through the next part of this. Until the next video comes out where we continue this, I hope you all have a wonderful rest of your week, and thank you all so much for stopping by.